Hello.
Hello.
Hi, Anton. Hi, Ivan.
Hello.
How are you? First of all, welcome.
Good. Thank you very much.
We have passed around 4 minutes already, but it's better that we start with this feed because uh, sometimes people want to join, but they cannot make it. We should give some room to people around like 5 to 6 minutes. Then start, I think. Already live for the last 5 minutes. So we already write down on the comment section, but I want to tell to YouTube viewers that it's better to change your video quality from automatic to high quality viewing section because in automatic mode the screen resolution will be very low, so it may not be visible for you. So please try to change it, either your mobiles or your desktop. And in any time, you can comment your questions, and we are going to collect them, and we will make a questions and answers section at the end of the webinar. We will try to answer your questions. Yeah, that is all for now. Let's check. Let's remove the screen, Ivan, for now. Okay, I removed it. Let's wait a little. In the meantime, I'd love to introduce myself and ourselves, actually. We are RhinoCenter, hosting the webinar with engineering team. We are actually based in Istanbul, Turkey. We have been doing the corporate trainings along with software sales. We are an official reseller of RhinoCenter software and also some other plugins. For this webinar, also I shared the links for the software and the plugins to download. The Rhino evaluation version and other plugins are already in the description, so please check. And also, I'd love to hear. What you do, how you do. Would you describe your company, your initiative?
Definitely. Let us please share our screens, and we will tell you a bit more about this. So, yes, a second. Okay, so we're going to start with a short presentation, and let me. Sorry, I always forget how to do this. Sorry, present. Okay. Yeah, basically we at Engineering, it's me and Anton Koshelev. Anton, maybe you want to start?
Yeah, sure. Thank you. Yeah, we are architects and computational designers, and we co-founders of Engineering. We work with other companies. We provide computational design support and parametric consulting. So basically, we provide some online training and consulting. We are working with projects which require parametric approach. And of course, we're interested in sharing our knowledge and our expertise.
Yeah, also you can check our works and our courses and everything on our Instagram, our website, and so on. This webinar is going to be the first in a series of online events, which are going to be dedicated to the topic of subdivision modeling in Rhino and in Grasshopper particularly, and the application of this knowledge for your projects, or both educational or commercial. We start this series from two free webinars. One of them is happening right now. Another one will be happening in a week, where we will prepare you for the following workshops, if you might be interested in joining them. We will cover the basic topics such as Mesh Topology, SubD tools in Grasshopper, such as data management, and all the necessary tools which will allow us to advance a bit more in the following workshops. We have already conducted a workshop about this topic. It was quite an interesting experience for us, and I think it was it was very nice to see the works of the students as the final outcomes, and we would like to move it forward, and that's why we are organizing these two free webinars, to make sure that the audience is already prepared and we can go a bit more with the design and everything. Mm-hmm. So I think in 1 minute, correct me if I'm wrong, Mustafa, please, if we can start the actual presentation, actually we can start talking about the theory and other parts of our webinar.
Yeah, I mean, already 10 minutes passed. I think it's okay to start. If anyone from now on catches, I don't think they will miss so much, because there will be also an exercises
sure.
session at the end of the
sure.
presentation. So it's better to start.
Great.
While you are presenting, I will remove myself from live section. Mm-hmm. I will try to follow any questions from YouTube. Mm-hmm. In any case, if you need me, just give me a heads up and I will be here.
Great. Thank you very much.
See you.
Yeah, just a couple of words about the organizational moments of this webinar. I would like to ask all of the people who are watching us right now, please, if you have any questions, post them on the chat on YouTube. We will check them in the meantime, and in the end of this webinar, we will have like 20 to 30 minutes of Q&A session. We will start with the theoretical part behind this topic, so that you are aware of not only the commands and components in Grasshopper, but also in the theory behind it. And then we are going to show you 3 different exercises, concentrating on how to achieve controlled, precise, and rather simple geometries achieved with SubD modeling tools from Grasshopper. And yeah, then we're going to have a Q&A session. So as Mustafa just said, let's go ahead and let's start our webinar. So first of all, I would like to talk about the terminology. Don't be scared by the vast amount of text. You will be able to rewatch it and check it if needed. Basically, working with SubD is very similar to working with meshes, but at the same time, it has some really useful features of NURBS geometry. It's like something in between, which combines the benefits of both mesh and NURBS geometries. So Rhino SubD, basically, as you can see here, it's a new geometry type, which is presented in Rhino 7, which hasn't been available before. We're going to work with some elements of SubDs, such as edge loops, which is, as you can see here, the definition. I'm probably not going to go through all of them, but basically all of them are going to be used by us in this webinar. We're going to create a base mesh, which will be the base for our SubD geometry, and so on. And we will show you how to create different types of hard edges, of freezes, of so on. And these are the terms such as vertex valence, naked edges, crease, mesh pole. These are the terms related to mesh modeling. Again, you can rewatch this, or you can read a bit more about this in some forums or some literature dedicated to the polygonal modeling. Yeah, there's a lot of theory and stuff about this on Blender or Maya or Rhino forums related to polygonal modeling. But we are going to concentrate particularly on Rhino because this is our topic. So yeah, let's go ahead. There are, as mentioned before, there are 3 types of geometry in Rhino, which are NURBS, which is the main function, basically, of this program, which allows us to get very precise, mathematically defined shapes. There is a mesh, which is widely used in Grasshopper, and actually Grasshopper has a lot of potential in working with mesh whenever you want to achieve some organic shapes or make some analysis, some calculations, even topological optimizations. We work with mesh because it's lighter than NURBS geometry. And finally, there is a SubD, which, as I mentioned before, kind of combines the features, and I would say the best features of NURBS and mesh alike. So what is a SubD in Rhino? Well, as in many other software, subdivision is basically just adding more polygons to the model, making it more smooth by increasing its complexity. But in Rhino, SubD objects are high-precision spline-based surfaces, and therefore they allow us to have the same control as a mesh and same precision as NURBS geometry. So it's basically not an ideal, but as close to ideal as possible way to create complex freeform shapes and create them in a rather simple manner. Why do we use the SubD in Rhino? Well, first of all, sometimes it's very hard to achieve a certain shape using the NURBS geometry. For example, the Y connection, where you have three let's say, columns meeting in one point, or three branches meeting in one point, might be very topologically difficult to create such a shape, but with SubD there is no problem at all. It also allows us to create highly accurate and very quickly editable organic shapes, which are so loved by many designers and architects nowadays. Another huge benefit is that we can convert these models directly to manufacturable solids. Like for any industrial designer or architect, or if you want to make your model or prototype, you can directly use your SubD model to 3D print or to CNC mill it, or any other fabrication technique you want to use. And finally, the SubD is widely applied for reverse engineering functions, which are not going to be covered by this webinar, but which is still a huge field to apply this tool, where you can make a scan of a certain detail and get a clean quad mesh out of it in Rhino. Yeah, here you can see some of the applications of the SubD in architecture, industrial design, animation, 3D modeling, and so on. As you can see, there is a hotel by Zaha Hadid. There is a car interior from official McLean website, which was made by Carter TG. And then there is another model you can see as well. So the goals of today's webinar, the first and foremost, is to prepare for a series of hands-on workshops in parametric SubD modeling, basically in how to model with SubD, not only in Rhino, not only by hands, but how to automate this process and how to create parametric shapes applying the SubD technique in Grasshopper. Then we need to learn how to create clean. First of all, basically, we need to learn how to create clean and correct quad meshes as a base for our SubD. And finally, we are going to master the skill of achieving complexity from very simple base forms. So what I mean by this is that we are going to make very simple, very controlled, quite edgy shape and convert it into something very smooth and something very sophisticated. This is probably the most important slide of today's presentation, which is the brief explanation of a SubD workflow, which we are going to use. It looks a bit too much, but in fact, it's rather simple. We normally start from, we are actually going to be using all three types of geometries. So it's going to be, we're going to start with NURBS, convert it to meshes, and then convert it to SubD. And in the end, if we want to fabricate it, we're going to convert it back to NURBS, actually. We start from creating the basic curves, which basically define the shape we want to achieve. It can be either a surface or a grid or something else. Then we actually create this, define the size of our mesh. We convert it into we create lofts or ruled surfaces, some which can be easily converted to quad mesh. We apply all the modifications we want to achieve. For example, if we want to achieve hard edges somewhere or creases, or if we want to get our shape deformed not uniformly. And then we convert it to mesh directly. Then we can apply some patterns. For example, if we want to create a grid or create some variation for our shape. We bridge these layers after that, so that we can create a solid SubD object. We join it, and in the end, we convert it to a SubD. And then, yes, as mentioned before, if we want to convert it to fabricate it, we just convert it to NURBS again, and we receive a very precise and very clean NURBS geometry. Basically, what are the key principles which we need to keep in mind while we start working with SubD? Well, first of all, it's very similar to the principles of any polygonal modeling. First of all, you need to keep the least number of vertices possible. So keep your mesh with as few vertices as possible, so it's not heavy. Space the edge loops evenly, so that there is not such a thing when your mesh face is very long or very narrow at some point. Use quads as a base mesh. Try to avoid triangles as much as possible. It's not critical for SubD, because SubD can work with triangles, but still it's much better to use only quads. Try to avoid non-matching base meshes, so that you don't have naked edges where you don't want to have them. It's important to have your base mesh very clean and welded. Use mesh transitions while locally creating a denser mesh. So you need to make sure that your edge loops are continuous, and you don't have points where some vertex doesn't match with another one. And finally, keep your data structured. The last point is particularly important while working with Grasshopper, because Grasshopper is all about data management. So it's very important to keep it clear and controlled at any point of your workflow. Here you can find these points explained a little bit more. So as you can see here, for example, the mesh become the SubD wiring, they become very dense, for example, here or here, but at the front part of the car, this mesh is pretty large scale, and it uses as few polygons as possible, which is actually the right way to do it. You can also see that these two meshes, although they look very similar in terms of shape, they still demonstrate a very different quality of the grid. So try to achieve more or less evenly spaced edge loops. Use quads wherever possible. Normally, it's almost always you can avoid using the triangle by using more, or actually sometimes even less quads instead, like you can see here, for example. This will also help to create, for example, a hard edge if necessary. Avoid the non-matching points, which you can see here, for example. Try to make them matching, and try to create points if necessary in the places where they are needed. Like you can see here, this is basically a diagram of how to use the transitions to locally create a denser mesh. Actually, if you can check this website, topologyguides.com, you will find this article, and you will find a lot of information about the polygonal modeling. So I highly recommend it. And finally, keep your data structure. This is an image from the Food for Rhino website, which was created by Daniel Piker, who is the author of Pufferfish plugin, which we are going to be using today. As you can see here, you have very consistent and very clean mesh strips, which is a sign of very clearly and correctly organized data, which is, again, a key thing in Grasshopper. Sorry for being repetitive, but it's a really important point I'm trying to make here. That's basically it with the presentation, with the theoretical part. And please drop any questions on the chat. And I think we can go directly to Grasshopper and start our first exercises. I'm going to go. I'm going to move aside. I'm going to start a bit fast, because if you want to repeat this, you can always pause the video or rewatch it later. But still, I will try to keep the speed relatively moderate, so that we can be on the same page, let's say. And I try to make sure you understand everything. So let's go ahead and let's start our very first exercise with the SubD. I'm going to show some very basic stuff in Grasshopper. Let's start with creating actually a very simple geometry. It's going to be a center box, which is a NURB cube or NURB box, basically. Let's give some values, like let's make a cube. Let's put equivalent parameters for x, y, and z. I'm going to do this, and actually I'm going to select all, select video off, and yeah. Okay. As you can see, we have a cube here, and it's a NURBS geometry, basically. Basically, it's a geometry which consists of fixed surfaces. So I'm going to deconstruct this VRAP and start adding the edges to this. But before we actually do this, let me show you how to convert this very geometry to something that can be, sorry for this, to something that can be very easily subdivided to a SubD. Basically, once we, sorry, I don't know what is happening, but yeah, okay, fine. So yeah, let's start preparing our base for our SubD. We need to convert all these faces into simple meshes, as you can see here, right? And after that, we need to join this mesh together. We need to say weld mesh. And I prefer to use the Weaverbird's weld mesh component because it allows you not only to weld, but also to join the mesh. So we can first join these mesh faces together, and then we can weld them. And after that, we can just say SubD from mesh. Function available in Grasshopper for Rhino 7. So yeah. You see that basically it is converted into something very similar to a sphere. Actually, topologically speaking, this looks very similar to a sphere, right? It's like
Ivan, one comment about, can you turn on bifocals, because they love
yes. Thank you very much for this. Actually, that's a very good comment. Yeah, of course. Sorry about forgetting this. Yeah, now it's better, I guess. All right, so you can see that if we apply subdivision directly to a cube, it basically gives us just a sphere. That's kind of nice, but normally we want to achieve something more designed. We want to have more control of the design. Now we don't have any. So that's why we need to start introducing some more edges, actually edge loops to this basic geometry. I'm going to keep this somewhere here and preview it for the moment. And let's see how can we actually start adding more control and more detailing to this geometry. Well, first of all, we can, even before we use surfaces, we can just use a tool from the Weaverbird plugin, which is called Weaverbird Catmull-Clark Subdivision, or Weaverbird Constant Quad Subdivision, or even a tool from Kangaroo, which is called, I think it's called Refine. I mean, at least in the previous version, it was called like that. Yeah, it's this one. So yeah, as you can see, it just adds more divisions to this geometry. And let's use another SubD, and let's see how will it change the shape. You see that it already gives us something more let's say angled. So if we compare this shape to this shape, we see that they are very different. And we just made one more operation. We just subdivided each part into each face into 4 faces, right? If we increase the level of subdivision, and here by subdivision, I mean, I know it's a bit confusing, but here by subdivision, I mean the more traditional understanding of this notion, which is basically just dividing a face into, like using kind of fractal-based algorithm, dividing a face into 4 faces, or 16 as now, or 64, and so on. And you see that with each subdivision, the shape becomes more and more rigid and more close to the first, closer and closer to the first initial geometry, right? So we already see that we can achieve this kind of control and this kind of more rigid geometry by simply increasing the subdivision. But what we can see, what we can also see, is that this geometry becomes very, very heavy. You see that it has already 1,536 mesh faces, which is a lot for such a simple geometry, right? So we came up with another solution, which is much more simple, but actually allows us to achieve a very similar, in a certain way, even more controlled result. We start working with NURBS geometry with surface in this case. And we are going to use a tool from Pufferfish plugin. Here you can find it in Surface. The component is called parameter subdivide surface. What does it do? It's basically very similar to the isotrim component from default Grasshopper, which basically allows us to divide the shape in certain number of faces, right? And as you can see here, it uses the parameters in U direction and in V direction, right? So what can we do here? Basically, we can just provide the values that we want to achieve here. So as you can see, now we have 0, 0.25, 0.5, 0.75, and 1, which is basically the domain from 0 to 1 divided into 4 parts. As you can see here, I'm going to hide this thing so it doesn't confuse us. You see that it divides each face into 4 by 4 faces, right? Which are surfaces. So this means that we can actually provide these parameters instead of using the default ones. We can provide our own parameters. I'm going to use the merge component so that we have a more structured data and we don't get confused. I'm going to provide a 0 as the first parameter and 1 as the last parameter, because in any case we will have the points on the ends of our surface, right? So. And then I'm going to add one more division in between. I'm going to use, actually, I'm going to have 2 points in between so that we have support loops from this direction and from this direction. And let's use something like, let's create a slider from 0.001 to 0.499, which is something in between the edge and the middle of our surface. I'm going to connect it to D1. And what I'm going to connect to D3 is actually a subtraction. I'm going to subtract this from the end, from 1, right? And I'm going to connect it here. And if we connect this thing to U and V of our geometry, you see that now we have a very, very thin edge, very thin face, very close to the edges of our cube. And if I move this slider, I can actually control the edge. And let's go straight ahead and let's connect this to our SubD. But first of all, we need to convert this to. I'm actually going to copy this thing. I'm going to convert these surfaces to simple mesh. I'm going to flatten the data. It's very important to flatten it also, so that we get one mesh as the outcome. And I'm going to preview this geometry. And I'm going to hide all the rest. So as you can see here, now we have only 54 faces instead of 1,536. But if you look at this geometry and this geometry, I'm going to actually hide the. I'm going to hide the mesh edges because they're quite confusing. It's SubD. Okay, sorry. With SubD does work. Okay, but still you can see that these geometries are very similar, but achieved with much more efficiency. And you see that the closer we move these edges to the center, the closer it gets to the initial shape, which was like sphere, something very similar to it, right? And the further we move it away, the more it becomes a cube, which we had before. It still has a very tiny fillet, which actually is a very good thing if you work in the scale of industrial design or product design or even with architecture. It's very good to have a small fillet, and here you can control it, right? So this is basically the central concept of this modeling. And the most important thing is that you see we always need to have these points matching, because I'm just going to give you an example. Let's see. If there is a mismatch happening somewhere, you see what we get? We start getting a very weird and topologically incorrect mesh. So that's the thing you need to always take care about and always need to take into account. Yeah, basically it for the first exercise. I'm going to structure the code a little bit so that you can actually, and I'm going to keep it for half a minute on the screen so you can actually, if any of you were repeating this, you can check if everything is correct. Or yeah, and also in the end, I'm going to answer your questions regarding this. So let's have like 20-second pause to actually repeat this, and I'm going to go on.
Hi again, Ivan.
Yep.
After that, we also have 2 more exercises.
Yep.
Okay, great.
Exactly.
Good to know.
I mean, this is just like explaining the yeah. Sorry, this is just explaining the concept, and then we're going to have an exercise about generating shapes that can be easily converted to quad meshes, working with basically thicknesses. And finally, Anton will show you a very nice exercise of modeling the spatial grid that you might have seen on the poster, and maybe even one more exercise if we have time. Let's see.
Also, we suggest that after watching the webinar, it's better to repeat it, right? Because it's like a preparation session. If you want to join the upcoming workshops, these information is somehow essential.
Exactly. Because our aim for the coming workshops is to concentrate mainly on the design and on creating some more advanced, let's say, workflows, which we normally apply at work or at some competitions, or to fabricate something. I don't know, but yeah, that's basically the idea. Okay, so once this is done, I think we can go ahead. Let me just. Yeah, sorry, I'm gonna just move this thing a bit down. Yeah. Okay, so let's go ahead. Let's hide this and let's start create a base geometry, which later on will be converted into the spatial grid into something much more complex than what you have seen right now. I prefer to do everything in Grasshopper because so that we can. We don't have to have a Rhino file attached to it. So first of all, let's construct a point. And we are going to go steadily from the simplest geometry to the more and more complex ones. So we start with a point. We construct a point in the center. I'm totally fine with it for the moment. Then I'm going to create an SDL line. Again, there are many different ways to create surfaces. And one is just an example. If you prefer to use something else like a rectangle or something different, please feel free to do so. Yeah, by default the vector is z, but I just want to put it here so it's understandable. Actually, I'm going to increase this to something like 100 maybe. Yeah, and let's extrude this geometry along the x-axis by something like 300, maybe I don't know, 300. Let's try. Let's start with this. Well, maybe it's even too much. Maybe 230. Yeah, not bad. I'm happy with that. So this is like the basic surface which we will be using for the following manipulations. And normally, how do we deform geometries in Grasshopper? Well, it's a very simple trick. We take an attractor point or attractor curve, and we deform the surface according to that. But actually, I'm going to show you another way, which is, in my opinion, much smarter and allows us to have much more control of over the geometry, which is going to be done purely mathematically, purely using the graph mapper and some other functions. So basically, here we need the surface only to get the normals, right? Of course, we can use a vector because, like, we work with planar surface at the moment. Still, I think it's better to do it this way. So first of all, let's divide the surface into the points, and let's use something like 12 points in. First of all, let's see what is u and what is v direction. So u is horizontal and v is vertical in this case. I'm going to use something like 27, let's say, points. Always try to make sure that your grid looks more or less like quad grid. By quad, I mean square. It always should be quad, but also try to make it as close to a square as possible. So make sure your future faces will be as uniform as possible, basically. And now let's start actually. Actually, we can do the following thing. We can do it even in a smarter way. We can just take the dimensions of our surface, right, like this, and we can make sure that our surface is as close to a square as possible. Let's not surface, but our grid is as close to square grid as possible. Let's make something like I'm going to use division, and I'm going to set the dimensions of the square to 5.0. Let's divide U. Let's connect it to U, and let's do the same for V, basically with the same value. Right. So now you can see that it's as close to a square as possible, which is exactly what we were trying to achieve. And now it's maybe a bit too large, but I think it's still fine. Okay, great. Now it's time for us to actually start generating the vectors for our geometry and to start deforming it, right? So first of all, I'm going to use this surface. I'm going to create a separate surface container for it, so that we don't have to have everything in one place. Always try to keep your code as clear as possible. I know I always fail to do this at my work and at my just like studies, but it helps a lot. So whenever I can, I try to make it as clear as possible. Yeah, let's do this, and let's start actually creating these vectors. Let's use the surface closest point. We use the surface as one input. We use the points as another input. And actually, we already have this UV coordinate, so we can just use the evaluate surface correctly. Yeah, let's just use evaluate. Let's connect surface here and UV here. Yeah, we don't even need this. Why are we doing this? Because we need the normals. We need this vector to match with all our points. So we need to get one vector per one point, right? Okay, so let's now wait. Let's hide this. Let's hide this, and let's go ahead. First of all, we need to move these points along these vectors. And to move this point not only along this vector, which is the normal, we need also to have the amplitude. Basically, how much are we going to move this point? In order to give the distance, we need to provide the amplitude, which is called exactly like that. This component is named amplitude. We connect the normal to the vector. That we need to connect some distance, some value to A, which is the amplitude. I'm going to connect this to T, which is the motion, and I'm going to connect these points to G, which is geometry, because we are moving the points basically, right? I'm going to hide this, and at first glance, it looks like nothing has changed, because actually almost nothing has changed. But this is just the beginning. Let's go ahead and let's start actually creating our motions, our values for the motion, for the amplitude. First of all, let's create a tree statistics. This is a component which is essential while you start working with data trees, because it basically allows you to extract all the data from the given data tree. It gives you the information about the path, about the length of each branch, and about the number of the branches, the total amount of branches, basically. Let's connect these points, or actually these UV will also work well because they have the same data structure, but doesn't matter. And let's start generating the values for our graph mapper. Because we are going to control the deformation of our surface by the graph mapper alone. And I'm going to use the sine function because it's it's nice, and I think it's really easily controlled. And also you can use the sine summation, which allows you to use multiple sine functions and to get even more complex results. But for today, we're going to do just sine. I'm going to graft these lengths, right? And I'm going to use the range to actually provide some values for this graph mapper. Let's connect this count to n, because we need to make sure that we provide a certain, let's say yeah, basically we have 41. Actually, I'm going to flip the matrix before, I think. Yeah. Let's see how it goes, and then maybe we will change direction, because I think that's might be nicer. Okay, let's go ahead and let's right click here and let's say x minus 1, because we already have 41 branch. We don't need 42 values. We need 41 values here, so that for each branch we have a specific value, right? And as you probably already know, if you are familiar with Grasshopper or with Grasshopper, basically, you already know that this almost always goes after the graph mapper, the bounds, and the remap. We're basically remapping the values that we generate here to some other domain we want to achieve as an output. In this case, I'm going to construct this domain, and I'm going to set it to something like from 1.2 0, let's say. Yeah, something like this. Very simple. And let's connect it here. And after that, I'm going actually to start this part, which is kind of it's not heavyweight maths. It's like very basic one, but still, I think it's better than vectors. And yeah, let's do this. Let's create. First of all, we need to graft these outcomes, so that for each branch we get a certain value coming from here, right? Because the amount of values we generated here is actually equivalent to the number of branches we had before. So let's use negative here. Let's use the construct domain again. Yeah, I'm going to connect this here. Now we're going to generate the number of sine wave we're going to have, right? So that let's put it at 6. And yeah, sorry, not like that. It's gonna be yeah. So we're going to do this, connect this here, and this will connect to here. And now I will show you what it makes to the shape, because it's better to see it once than for me to explain it 10 times. So I think it's better to see it. Yeah, let's use the range again. Let's connect this to the domain, and for the n, again, I'm going to say x minus 1 here. I'm going to connect those grafted values from the length of. Okay. And now what we need to do here, we already have the same number of values and the same data structure as we need for our motion to actually happen. But first, we also need to add one more thing. We need to add the expression, which is located here in a tab called maths, script, expression. Let's rename the second output as A. And now we're going to actually create the amplitude for our motion. So this was the function which basically tells us which, basically gives us the shape of our deformation. And here we actually give the amplitude of this deformation. So I'm going to connect something like 5 to start with to A. And as you see here, it immediately is highlighted in red. But don't worry, we left click here. We delete everything from here, and we type A times sine x in brackets. So, and now we just need to provide these values to x, which is going to be the x. And A is why it's called A, because I mean the letter is selected because we use it for amplitude. That's why I call it A. And as you can see, you immediately get this very nice deformation, right? I'm not sure if I'm happy with this. I mean, I'm quite happy with it, but maybe it will give us a nicer result if we actually flip the matrix, if this wave is actually going in horizontal direction rather than in vertical. So just yeah, let's just move everything after this point. Let's just take it, move it to the right. And here for the points and for the U and V, I'm going to use the component which is called flip matrix. It's basically just going to flip our horizontal direction of the surface with the vertical direction of the surface. I mean, I know that you all know this because it's like one of the first tools in Grasshopper. So yeah, basically, as you can see here, we had 41 branch. Each of these branches was consisting of 18 items, and now we have 18 branches, each of them consisting of 41 items, right? So as simple as that. And we connected here, and now you see we get this nice twist. And I honestly prefer this geometry much more than the previous one. So I think, but again, you are free to use whichever geometry you like. It's up to you. Just a matter of aesthetic. Okay, so yeah, you can see I'm going to actually share my screen like that, so that those of you who want to repeat can do so. And I'm going to keep it for I don't know, let's say half a minute. And yeah, just actually structure this a little bit better, and let's do this and let's move ahead. So yeah, let's do it like this, maybe like that. It's well, yeah. Sometimes if you have some troubles with like I do here, for example, you can just create a relay, which is going to help you to keep your code more clean and more understandable. So like that, I think it's cleaner. Let's say. All right. Yeah. This is it. I think maybe we can actually decrease this deformation slightly to something like this. That's 12. So basically, just to sum it up, what we are doing here is that we make sure that each branch has a certain amount of values applied to it, which allows us to have this kind of wave, right? That's why we don't flatten our data. We generate the values per each string of points, let's say. So we don't generate the whole points at once. We do it in a more structured way. And actually, as a general advice, it's always better not to flatten your data in Grasshopper unless you absolutely have to, which sometimes can be the case. And actually, it's quite often the case with meshes when you need to weld or join everything. But in this particular case, I don't recommend to flatten the data at any point, because we don't need it. We need this data structure to achieve these complex results. All right, let's actually see how this works a bit more. I'm going to again to hide this a bit. And
Ivan, one question.
Yeah, sure.
The left side of the definition is not, I think, visible. Yes, they would love to see if there is a comment.
Ah, sure. Yeah, I was just thinking that the left is already done, but okay, let's keep it like this for a bit more. Sure. Actually, I'm going to make it a bit more compact. Let's say like this. Yeah, sorry. I might be talking and showing a bit too fast, but again, you can always make a slower speed once you rewatch it, or you can also pause it and see this part of the code here as well. Yeah. At the meantime, maybe I'm going to group certain sliders and name them in a following way. This one is going to be amplitude. this slider is going to be the number of waves in horizontal direction. And yeah, and this is actually this graph actually shows us how many waves we have in vertical direction.
Okay. Also, can you were about to summarize the first two exercises? What are the expectations? What are the outcomes of these?
Oh, sorry. This is not the end of this exercise. Sorry, there is just like a bit more. Yeah. There's just a bit more to do actually to start generating the SubD, because now we just generated the base geometry, and now it's actually time to start working with Mesh and with SubD as follows.
Mm-hmm.
All right, so yeah, now let's go ahead and let's see actually what these parameters affect in this shape. You see, this affects the deformation, right? This one affects the number of waves we have in horizontal direction, right? And this graph affects the number of waves we have in vertical direction. So yeah, that's it. All right. Now, once we have these points, we need to actually start building our quad meshes from this thing. The easiest way and probably the fastest way would be, sorry again for that. The fastest and easiest way would be just building a surface from this. This is literally how this component is called. Sorry, I think I need to change something. Okay, yeah, it's better now. Okay, first of all, we need to flatten. Here we actually have to flatten our points. We connect these two points, and we need to provide the U count for the surface to be constructed. So we just take the U from here, but remember we flipped the matrix here. Therefore, we need to use, instead of U, we have to use the V, right? Because we flipped the matrix here. So let's do this. And also, let's not forget to go to expression and say x plus 1 for the surface to be constructed correctly. And as you can see, we achieve result, right? Now we can just apply the mesh surface component to this. I'm going to preview mesh edges, and by default, you see that we get quad geometry. And actually, now we can just use the same values we applied for U and V parameters here. So we can just take the number container, duplicate it. And now let's not forget to swap the U and V directions, because we flip the matrix. So let's use it for V and this for U. And now, as you can see, we get a very clean quad mesh of our geometry. But there is a problem here. You see that this and this and the edge, basically, the faces which are closest to the edges, they are quite deformed compared to those that are located in the middle. There are two ways to actually fix this. One of them is just rebuilding the surface. It basically does the same what it does in Rhino. It starts just distributing your points more uniformly, right? So you can see that now the grid became much more uniform. And if you don't touch the U and V points, it will basically preserve the geometry you had. So as you can see, I'm going to go to green mode and actually show you that it almost didn't affect the surface, except for these, like these parts. It doesn't affect our surface in, not at all, but almost doesn't affect it. So the shape stays more or less the same. And then we just quadrangulate it. There is another approach which can also be applied to it, is dividing it dividing the curves into these segments. I think now we're going to go with this approach because it's more straightforward and probably more easy to start with, let's say.
I'm sorry, I'll just jump in, and I want to add that the mesh surface has an equalize function at the bottom. You can invert it, and it does the same as rebuild surface.
Great. Yeah, guys. This is actually, so sorry, I forgot to mention this. This is a very good actually comment. And actually, it's not.
Yeah, they're not going to be the same, but
it's not. It doesn't do exactly what the reveal surface, but yeah, it's still a very good function. I mean, it's good. So yeah, let's do this, and let's actually start building something from this geometry. Let's start building a grid from this geometry, which can be later on converted to a SubD. So how are we going to build this? Well, if we are talking about making some, let's say, very simple quad grid based on on this mesh, what we can do, we can create two layers and basically make like a frame out of them, which can be built with SubD tools. So let's go ahead and let's use the offset mesh component, which comes from Mesh Agent plugin, if I'm not mistaken. If you don't have this plugin, an alternative can be just using the offset surface from here, right? Providing a certain distance, let's put it at something like 5 maybe, or maybe even 4.5, I don't know. Yeah. Okay, not bad. And then we just need to apply the same mesh surface component with the same values for U and V as we did for the other surface, right? So something like this. Why are we doing this? Because we need to have equivalent data structures for both of the surfaces which we are offsetting, right? Now we need to do a very simple operation. First of all, we need to explode this mesh. We explode it to make sure that each face becomes an item. And now we're going to actually start organizing the branches from these items. So we're going to make sure that each strip of these mesh faces is a separate branch of our tree. Let's start with the external surface, and then we are going to do the same for the internal one. We could have combined them both in one in one tree. I'm not doing this just to make it more understandable, let's say, because yeah, we're probably going to do this in our next webinar. But let's do this for this surface now, and let's actually create the branches. How are we going to do? How are we going to do this? Is we're going to use the partition list component. And for the partitions, we're going to use the, I think it's going to be U. Let's actually check how is the data structured at the moment. We create a list item component. And we see that the first item is here. Let's make a slider from 0 to 100. And as you can see, the data is structured in horizontal lines, right? So, okay, we just need to provide the length of U parameter, sorry, of V in this case, because we flip the matrix again. And now, as you can see, we have 17 branches, each consisting of 40 elements, right? So if now we will use the 3-branch component, I always suggest to use this to check how is your data structure structured. So let's use 3 statistics again. Let's use the list item. And let's connect our path to the list item. And of course, we connect it to path. And you see that this is our branch number 0. And if we make some more, you see, our branches go like that. Okay, that's exactly what we need. And now we actually need to split our tree to make sure that we have one branch which is kind of solid, and then the next 2 branches are going to be perforated. And we're going to repeat this pattern all along this tree. So how are we going to do this? Well, I'm actually going to keep this tree statistics component here. I'm going to use the split tree component to start working with this approach. I'm going to create another relay just for the sake of clarity of the code. And yeah, let's connect it to D, and let's use the cool pattern to actually split our tree to define which branches will be solid and which branches will be perforated. Again, we use the merge component to have more control over the pattern. Let's use the Boolean toggle with false. I'm going to say false, true, false. And there is another trick, how to actually make it more so that we don't have to use a lot of, let's say, zeros or ones or Booleans. We can just use duplicate data, or true, for example, and set it to something like 2. So that in this case, and also let's not forget to, in this case, it's important to flatten it at the very beginning, like here, at the input. And then what it lets us to achieve, you see that we get perforated parts, and we can control how thick will they be, right? So instead of typing it manually, we can just control the thickness of our, let's say, empty part in our code. And after that, I'm going just to use the cool pattern component itself for the positive paths of our grid. And I'm going to use the very same pattern for this, just to save some time, basically. So as you can see, we get this kind of perforation here, right? Okay, great. Now let's just merge this tree back so that we get this. Actually, I need to invert this pattern so that we get only these kind of connections. And now once we connected this thing, we get this grid, right? Let's hide this, and let's hide this as well. You see, we get this grid. Now we actually have to flatten this. This is the second time we are flattening. We use weld, Weaver bird, join meshes, and weld component here. Right-click, I say invert, so that it welds them as well. Just to be sure, I'm using another weld mesh weld vertices, which is a part of mesh utilities here, right? Just to make sure that even those vertices that are inside this tolerance, which are not matching perfectly well, that they are also welded. This is like just a play safe, let's say. For that, I need to unify mesh normals. Or mesh unify normals, doesn't matter. And this is our final mesh, which we can actually subdivide. But not yet, actually, because we also have to create the thickness to it. And there are actually 2 ways to do this. First way is probably the most straightforward. It's just to say offset mesh. which comes from the, and again, we can say the same distance as we did here, which is 4.5. And actually, that's pretty much it. We can already subdivide this shape. But the problem here is that we don't have the control of the creases. We cannot say that this geometry will be smooth or hard or whatever. We don't have the control. That's why we need to, first of all, we need to invert the create solid so that we just offset it, but we don't make a solid. So that we can actually make these bridges by ourselves in a more controlled way. But also, there is another approach. If you don't, first of all, if you don't have this component, you can just copy all these things, like basically everything before this component, except for the pattern. The pattern we can I think we can use the same pattern, and we actually have to use the same pattern, right? So we copy this thing, but we apply it to the offsetted mesh, surface. Yeah. So either way, which works better for you, just go for it. I think I will go with the offset mesh because it's just faster than copying this twice. It's just easier to use this component. And now we are interested particularly in mesh edges and particularly in naked edges, because naked edges are those that we are going to use to build these bridges. So let's put mesh edges for this mesh and mesh edges for this mesh. And after that, we have to join them. We have to use the join curves component for E1 and for E1 here as well. Let's hide this all, and let's see what we get here. This actually looks like a very good base for our bridges. So as you can see here, we have 66 and 66 polyline curves, which basically means that we have the same data structure. We have the same lists. What is left now is that we need to explode them. But as you can see, we get, instead of having a list, we are now having a tree, right? So we have each polyline started a separate branch, right? And it has all the segments in this branch, right? So what we need to do now, we just need to use the rule surface, and we also have to graft the A and graft B, so that between each two segments, oh wow, that's quite unfortunate. Okay. Well, I guess there was some mistake in not mistake, there is just some mismatch, but it's not a problem at all. We just need to find the closest mesh, closest polylines, closest to each other. That's actually not so. I mean, it's okay, but let's use it.
Ivan, I would use naked edge from Weaverbird component here, I guess.
Okay, that's a good
Let's
idea.
try this one.
Let's try this one first, yeah, because working with closest point is not always the ideal way.
Yeah.
Let's use the Weaverbird naked boundary, you mean, right?
Mm-hmm.
Okay, great.
Exactly.
Let's do it. This is the first, second. Let's try to explode them both, and let's try to see what we get. Perfect. Thank you for the suggestion. Yeah, guys, so this is a very good tool from Weaverbird plugin, which basically does the same what we did, but as you can see, it automatically sorted all the boundaries, right? So it's all correct. But still, we have to explode them and apply to the ruled surface. Okay, let me actually give you the last break before we finish, like for maybe 20 seconds again, and let's I'm going to delete this. So this part starts after the mesh surface, And here you have the pattern generation, you have the mesh welding. I'm actually going to join it in groups. Let's put this group. Let's put this as a bridge group. So this operation that we just did here with these surfaces is actually very similar to the operation from Rhino, which is called SubD bridge. Which basically, in Rhino, you select the one edge, another edge, and it automatically builds a bridge between them, like a SubD face. Or you can also select not an edge, but you can select a SubD face, and it will build this kind of connection between two faces. Here we are doing it with Grasshopper. It's basically same, but instead of selecting it manually, we have to make sure that our code selects it automatically, so it doesn't give us any errors. Great. So there is just one thing left before we actually convert it into a SubD, and we will be done with the second exercise at least. Yeah, also, again, sorry for repeating myself, but maybe those people who joined us later, please put your questions in the chat about this exercise. I know that we're going a bit fast, but we will be glad to answer them, basically, after this session, or any other questions, I don't know.
Ivan, there was one question from Martin. I think I pronounced it correct. He asked if the definitions will be available after the webinar.
Yeah, sure.
Okay.
I mean, I don't mind at all. If you agree on that, sure.
I think we'll put a link in the description for this video to the folder with all definitions.
Okay, great.
Yeah, definitely. No, for sure. I mean, it's of our interest to have people who go. I mean, it's always better if you go through this code step by step. We will also structure. We have actually the structured versions of these codes. It's just that we are doing them right now, showing them to you. But we have the structured versions, and sure, with all the groups and everything.
Also, there is another question. I can also, I think, share the questions on the screen like this.
I'm not seeing it at least. So, but
you're not seeing it. It's
I can see it. Okay, yeah, it says hello. In the video description, you put the links for the Heteroptera and Shortest Wall plugins. Do they work on Rhino 7 as well? Yes, they do. We are using them all the time. So please use them too.
Okay.
They do work, but I mean, there might be some. I heard that there might be some compatibility issues, but at least I haven't faced any in my Rhino, so I don't know. But there is definitely this. I mean, if there is any problem, I think it's definitely worth it asking about that on Grasshopper forum or on Food for Rhino. So there are always people who will be glad to help, and we will try to help as well. So yeah, let's see. Great, thank you very much, Mustafa and Anton, for passing these questions to me. If you don't mind, I will go ahead. We have just one part left before we finish this exercise, which is actually adding the creases. And it's no surprise that we are going to do it the same way we did it before. We are going to use the parameter subdivide surface from Pufferfish plugin. Just a quick, not a trick, but like let's say note that if you press Alt Control and left click on your component, you are shown where it is located. So please, if you cannot find something, you can use this command. It's pretty helpful. And here you can find it. It's a part of Pufferfish plugin. Okay, I'm going to connect this to parameter subdivide surface, and you see it's really heavy because I have a lot of them. But we actually don't need this much subdivision. We can do the same we did before. So again, for those people who might have not seen it before, I'm making the merge component. I'm creating the first value and the last value, which are 0 and 1. And I'm putting two values in between, which will actually define the position of my creases. So it's going to be something in between this value and a half of our surface. And then I'm doing another one, which is symmetrical, basically, value, which is 1 minus this value, which goes to D3, and 1 itself goes to D4. Something like this. Very, very straightforward. And yeah, let's connect it to U, and let's see if it helped us. No, I think it's the wrong. We need to connect it to V. No problem, we connect it to V, and for U, we use the, actually, yeah, I think it's correct. And we use the range with just 1 as the n. Basically, we need to divide this distance into one piece, right, like that. If we zoom in a lot, we see that there is another edge which is very, very close to the existing one. And if we start increasing this value, you see, we get this edge here, right? Which will actually provide us with hard edges. So for that, we convert these resulting surfaces into simple meshes, right, like that. I will hide this and this also. And yeah, after that, we can just merge everything we got so far, which is this mesh, the initial joined mesh, another relay here, the offsetted mesh, and those simple meshes coming from here. Then we need to flatten everything again. And as we did before, we use the weld, Weaverbird join meshes and weld. Right-click saying weld invert. Weld meshes, mesh weld vertices component. I'll hide this. And mesh unify normals finally. So that's SubD from mesh. And we are basically done. And now, if we apply the just to make sure it's more clear how it looks, I will apply the custom preview so that we have the color of this thing. We can actually tell how these we actually get these shadows, and we actually can control the sharpness or hardness, let's say, of this shape. So now it's pretty hard, right? You see that this fillet is very small. But if I start increasing this parameter, sorry, like this, you see it becomes smoother. Also, if we want to have a bit more control of let's say a bit, because now as you can see, it starts losing its thickness a little bit. But if we want to retain some part of its thickness, what we can do, we can actually, well, I think we have to do it here in this case. Yeah, probably. So before we made a mesh offset here after the merge, but before we make the mesh offset, right? We can use the parameter subdivide surface here as well, and provide. Of course, we can smash it. So we need to say meshed into poly surface. Yes. We provide range with only with only two divisions for U and for V. We get 2. and convert it back to a simple mesh. We flatten it and we connect it to the Weaverbird join meshes and weld. And I guess now we get something better. Yeah, so now, as you can see, we get a more, let's like this. Now our shape will not lose its sharp edges as much as it did before. See, it preserves the part of its shape, but it becomes more smooth. And also, if we, let's say, if we increase the offset for the mesh, if we increase this distance to something like, I don't know, 6, 7.5, you see, we basically get, yeah, we get quite. I would not say this is like the most sophisticated result we can achieve with SubD, but it's like a start. Yeah, and basically these ideas, they can be applied to anything. Just as the end of my part of this webinar, I would like to show you some just a couple of samples of what we did with this approach at our previous workshop. Of course, it was like a 2-day session. It was not half an hour. It was more time. But let me show you a couple of images. Yeah, for example. I'm not sure if any of the students who participated in this workshop, if they are here, but I think so. So they might be happy to see the results. Can you see my screen?
Yes.
Okay, great. So yeah, this is a project by Nicoleta. She was a student from our previous batch. Another project from Van Vithit. Project from Amir Ahmed. From Ioannis. Sotiris. And I think that's it. This is like what we're going to do now. So yeah, but basically I would say this model was the closest to the approach that we are doing now. As you can see, it uses the same logics, just more layers and more divisions. It was like more heavier model, but the approach and the logics behind it is the same. Having said that, thank you very much for the attention. I pass the word to Anton, who will show you another exercise.
Okay. I would love to cut in. There are 2 or 3 questions. Okay, Louise asked the location of SubD from Mesh.
SubD from Mesh is located in
the component.
Yeah, it's the default grasshopper component, which is located in Surface. It's located in Surface and SubD. It's a new tab for Rhino 7, so there is no such a tab in Grasshopper for Rhino 6. But in Grasshopper for Rhino 7, it comes as a default function.
Also, there is a question from Ivan, I think. Is there a way to specify edges as SubD crease with the SubD from Mesh component?
Yes, sure. You can. Yeah, let me share my screen once again. Sorry. Yeah. Okay. Yes, of course. You can here. So, sorry if I didn't mention this before. The default function here, you can say creases. If you right click and you say at mesh edges, it will it? No, 1 second. Yeah. So okay, it works with corners. So you can. There are no corners and no mesh edges. Okay, good. So yeah, in this case, you need to create the creases on your own, and the way to do it, actually, let me show you this way. It's again pretty straightforward. Let's say we just don't weld our meshes with our bridges. So we do this, but for each part separately, and we join them only after that. So let me show you how this works. We create separate mesh component for this mesh and for this mesh. Sorry, like that. Yeah, let's do this for each of them, like that, and also for the bridges as well. Let's just create another group. This, yeah, this. Okay, we need to flatten everything. Yeah, and then we apply SubD separately, right? We make sure to do we need to do anything else? I think we don't. Yeah, and now if we merge them and apply them to, we connect them to custom preview. What is it? Yes, here. Here we get creases. Yeah, like this. So basically, you just don't need to. Of course, you can join these SubDs after that as poly surfaces. You can join them as B-reps and get a NURBS geometry. But to get creases, you just don't weld them prior to that. That's it. Yeah.
Mm-hmm.
Great. All right, guys. Thank you very much once again. Anton, I pass the word to you.
Yeah. Thank you, Ivan. Hello, everyone, once again. And we will start with a new Grasshopper file, and I will just copy the first part of previous definition, right till the point where we reconstructed our wavy surface. So here it is. Let me preview it. Yeah. So I copied everything before this reconstructed surface. Right now, I'm going to triangulate it using Lunchbox plugin and Triangle Panels B component. Let's go through Lunchbox, Panels, and I'll use Triangle Panels B. I connect it to the surface, and I will put some numbers to V direction. Let's say 16 for now. Yeah, looks pretty good. I've got almost equal triangles. That works for me. Now I will transfer everything to mesh because it's still surfaces. I will use weld component from Weaverbird weld. But before this, I need to transfer these panels to mesh using simple mesh component. I'm going to mesh, utils, simple mesh, and connect everything. Pretty good so far. I will put invert option on weld component because I need my mesh welded. Yeah, something like this. I need to see mesh edges. Good. When it's done, I can extract dual graph out of this mesh. Dual graph is basically a graph based on the center points of triangulated mesh. Let's do it. I'm going to Weaverbird and I select Weaverbird's dual graph to get hexagons out of my structure. Maybe I will increase a bit the number of triangles. Pretty good so far. And after we did this, we can apply multi-pipe component. Multi-pipe is a SubD tool. It's located on surface SubD, multi-pipe. We have polyline curves in the dual graph. So before applying multi-pipe, I will explode every curve into lines. using explode component. And then I will check if I have any duplicates. I will flatten the explode component, and I will select remove duplicate lines node. Like this. Let's see. I have to 462 as input and 266 as output. Let's connect it to multiply. And I will provide certain inputs for it. Let's see. First of all, I want to do is a node size. Let's increase it a bit. Let's say to 20 or 70, even more. And you already see you've got a SubD around your curves. Like this. Then we can play with certain parameters, such as strut size. Let's try to change it. I need 0.5 for the strut size. Okay, that looks good. Looks good to me. Okay, and then we proceed with our basic workflow. We just showed you with mesh and surfaces. I will extract mesh from this SubD. So select mesh from SubD, this one. And I've got the mesh. I don't need to subdivide it, so I put division to 0. I need this rough mesh. Maybe I will increase the size even more, so it's more visible to you. And after we extracted the mesh, I will unify mesh directions using mesh direction component. It's written together like this. Then I will explode this mesh to get every face separately, and I will apply a parameter subdivide surface to them. So let's do it. Explode mesh. Mesh explode. In order to make calculations faster, I will reduce number of triangular divisions, so it doesn't overwhelm my PC. Let's say I'll put 13 in E and 7 in U, something like this. Let's get back to the end of the code. After the mesh explode, I will need to transfer every mesh face to the polysurface using Mesh Topology component. Mesh Topology, here it is. Okay, now I have only surfaces, which I can subdivide. I'm going to use parameter subdivide surface. Here it is. And I will not subdivide surface in one direction, and will subdivide it with one with one curve in the middle, another. Let's do it. I'm going to do it using range component. With one step for, let's try U direction. Actually, for V direction. No, one step for U direction and 2 steps for V direction. And I will increase the number of steps like this. Yeah, and here we go. You see that the surfaces are divided now only in one direction. And after that, we can transfer it to the simple mesh. And combine and clean them. As well, I'm going to use Weaverbird join mesh. Weaverbird join meshes and weld. Again, I need to flatten everything in the input, and I need to invert weld parameter. So my mesh is welded. Perfect. Once it's done, I'm ready to create SubD from the mesh. Let's do it. And here it is. I will apply custom preview. So the geometry is more visible to you. And change the number of steps into range component. I can control the sharpness of the edges. From pipes to actual hard edges. Okay, let me show you this part of the code more closely. So you could repeat. Okay, we have one more exercise to do, which is actually a nice one and quick one. I think we have time. Let's do it. I will group my previous exercise, and for this time, we will start with the simple box. I need to turn preview off. Good. Now for this exercise, let's start with the box. I'll go to the surface primitive and I will use center box. I will put some values, let's say 100, 100, and 100. Then I will deconstruct this box to get top and bottom faces. What we are going to do now, we're going to create a coral inside this box using multi-pipe component. It's gonna be super interesting. I'm deconstructing this box and I extract top and bottom faces out of it. I'm using list item and I know that my bottom face is gonna have index 4. And my top faces is gonna have index 5. Like this. Also, I will populate the box with points. Go into the Vector tab, Grid section, and I select Populate 3D. Let's create a big number of points, such as 1,000. Great. Once it's done, I would like to create a proximity between these points in order to get the line structure, line grid inside. You can use any kind of, any different type of grid, not necessarily proximity. You can use Voronoi, you can use even rectangular grid. But in this case, I'm using proximity 3D to achieve this kind of structure. A more or less random one. Okay, good. Next, what I need to do, I need to create random points on the top face of the cube. Let's do it again. Now I'm going to use Populate 2D. I provide my top face as an input for a region. And as number of points, let's say 500. Or maybe less. Let's reduce it to 70. Good. And what about the bottom face? Here we will create a point which we're going to control, the position of which we're going to control. I will do it using evaluate surface component. I connect it to list item and I simplify the input for the surface. Simplify and reparameterize, sorry. Something like this. Right click and set reparameterize in order to provide a domain to the surface from 0 to 1. As for UV input, we're going to use MD slider, which is located on input tab of params section. And within MD slider, we will be able to control the exact position of the point on the bottom face. Like this. Now, I will construct lines from every point on the top surface to the one point on the bottom one, using line component. And 2. So now you see all the lines are following this point, which is great. And we're ready to create the shortest walk throughout our proximity grid from top points to the bottom point. Let's do it. First of all, I need to filter my proximity grid. So I will remove every duplicate I have here using remove duplicate component. Remove duplicate lines. Again, I need to flatten the input. As an input, I had 5,000 lines, and I left with the half of it, almost half, which will simplify our solution. Good. Now I call for the shortest walk component. And for this component, I need to provide my grid and my lines. Oh, sorry. Not here, here, lines. And if I turn off every preview I have, you will see there are already certain passes forming throughout the grid. You can play with it as much as you want, and we will continue. Again, I need to remove every duplicate of the shortest walk I have. So I will explode every polyline after the shortest walk using explode component. And again, I will remove every duplicate from the explode component. Like this. Now I'm ready to construct multi-pipe. Let's go for the multi-pipe component. I connect curves to the curves input. I adjust the node size. Let's say 12. I will use decimals for more precise control. And it looks nice, but not nice enough. So we will complicate our structure even more. We'll create the thicker mesh pipe on the bottom and thinner on the top. And we're going to do it using points from our curves. Let's find all the control points. For curves, I will flatten the list and I will remove duplicates using cool duplicate points component. I will leave one point in place. Let's see. Okay, yeah, twice less. Perfect. Now I will need to sort my points from the top to the bottom. We will do it using the construct point. Component where we have that output, which refers to the z value of the point, z coordinate. And I will simply sort it. Key points. Actually, I don't even need to sort it because I can use list normalizer from GitHub. These components provide me a list in the domain from 0 to 1 from any kind of numbers I provide. Okay, and when it's done, I'm using graph mapper. These numbers in order to control the thickness, the gradient of thickness inside our SubD pipe. Okay, good. Let's remap output numbers using remap numbers and bounds. The bounds we have already from 0 to 1, so it's not necessary to provide any here, because by default they're from 0 to 1. And what we need to provide is target domain we're going to remap into. I'm using construct domain. For the target. And let's see. I need a bigger one as a start of the domain, the bigger number, let's say 30. Maybe less, we'll see. Yeah, let's put 10 for now. And as a domain end, I will use one. Good. Now I want to connect size points from pool duplicates. So these are my control points of the geometry. And for the node size, I can provide a list of my remap numbers. Let's do it. Yeah, it looks like this, and I need to reduce the upper bound of my domain in order to make it nicer. Let's reduce the top part. And let's elaborate it a bit more. I will change strut size a bit. Let's say I'll put 0.5. Yeah, looks even nicer. Okay. And also we can use cube feed in this option. What cube feed does, it basically places a cube, you see, right? SubD cube in the corners of your geometry, the breakpoints. Sometimes it looks nice, and sometimes you need it due to topology of the mesh. If you want to create a nice mesh strips, a cube feed will help you. And also we can work a bit with end offset. Let's see. The end offset. Maybe also work for us. Let's preview it using custom preview. We are not going to add any creases here because the topology of the mesh, topology of this SubD is not perfect. And you can put creases only where you know that you have a proper mesh strips and you know the mesh faces directions. Here is more or less random, so we're not going to do it. We can work also with gradient a bit. And of course, we can play with the base point, changing it. And every time we'll get different result. Okay, that's it for today. I'll leave a code on the screen for a minute, so you can follow. And if you have any questions, please write them into the YouTube chat. We will answer.
Yeah, in the meantime, a bit of self-advertising. If you have any other questions after the webinar, if you want to ask anything or have any ideas or want to apply for the workshop, please DM RhinoCenter or us in generic whenever you want. We will be glad to answer and help and also we'll be happy to see you at the upcoming workshop. So yeah, in the meantime, please send us your questions. We'll be here for, I think, 10 to 20 more minutes. So we'll be ready to answer them.
Thank you, Ivan, and thank you, Anton. Also, it should be better to inform the attendants that this is the first webinar of two-leg webinar series, free webinar series, which then will connect to a series of workshops. So the next one will be next week. Yeah,
next Sunday.
One,
yeah.
Next Sunday is the second leg of the webinar. Then continue with the workshop. It's better that if you are going to attend to the next webinar, it's better that you watch this webinar again maybe and repeat whatever we did, just to get some basic idea about the SubD tools. Also, if you have any questions, like said before, you can write down to the comments. We will wait a little for any possible questions. Then we will thank everyone.
And maybe in the meantime, we can also tell a bit more about the workshops. The workshops are built in a modular way, so that the first one will be dedicated to developing the design. Basically, it's like working with forms, working with concept, building your base geometry, and so on. We of course thinking about SubD modeling workflow. The second webinar will be, the second workshop will be concentrating on the detailing of the design. It can be this design or any other design which you want, but it can be design that comes from the first workshop, or you can come for the second whole workshop with your design in mind or whatever. And it will be concentrating more on detailing your model basically in detailing. And the last webinar will be about preparing your model for digital fabrication, either 3D printing or CNC milling or robotic fabrication. This is still to be confirmed, and we will be posting more information as soon as the dates approach. Yeah, I think that's pretty much it.
Mm-hmm. Yeah. It seems that we already answered the questions while the webinar was on the go.
Yeah.
I think we can allow people to write questions in the chat after the webinar is done, and next week, we will answer them as well.
Yeah, sure.
So we will accumulate them and.
Okay, that's correct. For now, that it seems that there is no question. I think next week there will be, because people are going to repeat the steps that you already make. Maybe they will stuck on some points and prepare some questions, collect some questions. Next week we can also follow the questions.
There is actually one question I see about how to register on. Well, first of all, thank you very much for the positive comments, guys. There is a question how to register for the webinar on the 28th of March, and also how to follow us. Should I share our Instagram account, Mustafa? Right?
Yes, sure.
Right.
I think it's in the description for the video.
Yeah, I already put in. In the description page.
So please, everyone, check description.
For the registration of the next webinar, we will also create a registration form today. You can check it through our profile, RhinoCenter profile. Also, we are going to announce it through social media accounts. So the form will be online today. And we are going to send the next webinar's link who already registered to this one, of course. just check your mails. Okay. It seems that we are okay. If you have anything to say, I'm listening and we are listening.
Yeah.
Yeah, there are messages thanking. Thank you for the attendance. Thank you.
Yeah, thanks, guys. We're very glad if it will be helpful for your future projects. So yeah, great.
Okay, let's finish it then.
Yeah.
If you have any questions, I mean, next week we can follow it up.
Great.
For sure.
Okay, Ivan, Anton, thank you very much for the great opportunity and the great insights and the webinar. Everything was okay and perfect, actually, not okay, far from okay.
Thank you for inviting us. It was a pleasure to do it with you. So thanks.
Thank you very much.
Our pleasure. Next week we will see you again. For now, have a good day or good night.
Thanks. You too.
Thank you.
Okay. See you later. Bye bye.
See you.
Thank you. Bye.